Simon, and welcome to my crib. Oh, I'm dizzy. I'm Simon, and welcome to your next lesson. However, first, I want to tell you guys something cool about me that I didn't realize was cool, but I guess it's kind of cool. I am an artist. So I drew this alien girls. Well, I drew and then painted them. I'm a watercolorist, and someone suggested that I just start showing my paintings in videos. So I will probably start doing that. So expect to see some paintings in the future. 5, day 2. Today we're talking about the infamous, the famous, the amazing cladograms. Let's get into it. So our lesson objective is that students will be able to understand that cladograms are shared characteristics, which means two organisms are going to have the same characteristics. They're going to share a characteristic. Students should also be able to evaluate evolutionary relationships between organisms based off of a cladogram. So by the end of this lesson, you should be able to look at a cladogram. First of all, recognize, oh, that's a cladogram. I know what that is. And then you should be able to tell me, okay, this is the common ancestor. Okay, this organism has this, this, and this, and whatnot. So let's get into it. Okay, so first things first, we're going to watch this recap video about classification that'll lead us into our discussion of cladograms.
From amoebas to aardvarks and fungus to fruit trees, what does it mean to classify organisms? Why do we do it, and how is it done? Classifying anything simply means to put it into a group. In terms of biological classification, organisms are classified or grouped with other organisms that they are most closely related to. These small groups are then classified together into larger groups, and so on, until we reach the top level of classification, which From amoebas to aardvarks and fungus to fruit trees, what does it mean to classify organisms? Why do we do it, and how is it done? Classifying anything simply means to put it into a group. In terms of biological classification, organisms are classified or grouped with other organisms that they are most closely related to. These small groups are then classified together into larger groups, and so on, until we reach the top level of classification, which places organisms in one of 3 biological domains: archaea, bacteria, and eukarya. When each organism is classified in this way, it allows scientists to see the relationships between different species and make sense of a hugely diverse array of life. Modern systems of biological classifications, or taxonomy, are based on the work of a pioneering 18th century scientist called Carl Linnaeus. By studying hundreds of organisms, Linnaeus devised a method of grouping them according to their shared physical features. Those with similar physical features could be classified together. The most similar organisms, i.e. those that could breed together and produce fertile offspring, were designated as belonging to the same species and given a Latin species name accordingly. For example, all domestic dog breeds belong to the same species called Canis lupus familiaris. Other members of the dog family that are closely related, but not the same species, will share the higher group name, the genus name, but have a different species name. For example, the grey wolf, which is the closest relative to the domestic dog, is classified as Canis lupus lupus. By using this system, we can classify organisms according to their shared evolutionary history. Linnaeus also created higher and more inclusive taxonomic categories that encompass an increasingly broader range of organisms. The structure of Linnaeus' taxonomic groups can be seen here. You can make up a little rhyme or acronym to remember this, such as keep ponds clean or frogs get sick. By using this system of common groupings, we can develop diagrams that show the interrelatedness of organisms based on their morphological diversity. For example, this diagram of a taxonomic tree shows that humans are more closely related to chimpanzees than they are to gorillas. A common ancestor is represented by each split in the branches of the taxonomic tree. How long ago did humans and gorillas diverge from an evolutionary perspective? Recent advances in science, including the ability to categorize DNA sequences, have enabled scientists to accurately determine how closely species are related to each other. This has led to the revision of the original grouping suggested by Linnaeus. New organisms are constantly being discovered, and relationships between organisms are changing all the time, so the importance of a taxonomic study to modern science cannot be underestimated.
All right, so taxonomy is extremely important. Oh, no, next slide, please. So, our warm up. What is taxonomy and why is it so important? Exactly. So taxonomy is going to be the classification and grouping of organisms based off of their shared evolutionary histories. And it's very important because it allows scientists to not only organize information in order to study it, but also allows for there to be open communication between scientists in different parts of the world who maybe don't even speak the same languages. So taxonomy is very important because again it gives that scientific name to every organism that we've ever discovered as scientists. So I'm gonna read this to you. Plants known as bluebells exist in England, Scotland, and the United States. In each of these locations, however, the plant known as a bluebell is very different from the plants called bluebells in the other two locations. Okay, so a bluebell in the US is this flower, while in England and Scotland, they're two totally different things. Even though all of these places speak English, even within the same language, the common names can be reused and recycled, which is why taxonomy is so important because it gives a specific scientific name, a two-part scientific name that is unique to this organism and this organism only. A different scientific name that is unique to this organism and only this species. And same thing here. Okay? Every type of organism, every different species has its own two-part name, and that is so we can communicate easily between countries, across generations, and so forth. Okay, so again, taxonomy is the entire field of science that studies, classifies, and names organisms. Okay, and if you remember this dude right here, he was Swedish. His name's Linnaeus. Don't know how to pronounce it, but that is him. He is the father of taxonomy, and we study about him today. Obviously, we are doing that currently. So, taxa is a taxonomy, is a taxonomic category or group. So, for example, you would say a domain Eukarya is a taxa. Kingdom Plantae is a taxa. Kingdom Animalia is a taxa. Phylum Chordata, order Primate. Family, genus, and species, these are all different taxonomic categories or groups. So if they ask you which taxa is more specific, which taxa is less specific, that is just talking about which category, which group. Is it the kingdom, phylum, class, order, family, genus, or species? Okay. Binomial nomenclature, using the two-part names, right? So again, bi means two, nomial, name, nomenclature, name system. Two-part names. Okay, so system of naming all organisms on Earth using two-part Latin names. So a common name for this organism, like if you saw it on a beach, someone might say, oh, that's a pebble crab. Well, the scientific name is actually Xanthias lamarcki. Okay, and also remember about the scientific name, the first part of the scientific name is always the genus. There's always a space. Then there's a second part of the scientific name that is always the species. So let's look at some more examples. Reviewing. This right here is a human. Okay, humans are called Homo sapiens. Homo is the genus, sapiens is the species. This right here is a puppy. That's the common name, is puppy or dog. The scientific name is Canis familiaris. Canis is the genus, familiaris is the species. Okay, let's look at this example. If I tell you this organism, that an organism's name is Hippopotamus amphibius, what is the genus of that organism? What is the species of that organism. Exactly. The genus is always this first part. The species is always the second part. Always. It's always like that. It's so easy. I love it. Binomial nomenclature. So we have two organism names here. We have Panthera leo and we have Americano leo. So true or false? These organisms have the same genus. False. Genus, species. Genus, species. Are these the same word? No. Are these the same word? Yes. And these are both referring to the organism species. Okay, two more organisms. We have Vincia rosea and Vincia purpuro. These organisms have the same exact what? What do they have? The same genus, same species, or the same both genus and species? Genus. Again, genus, the organism species. This organism's genus, this organism's species identifier. Okay, so if these organisms have the same exact genus, which we know that because, again, that name, Vincia, these are the same genus. What else do they have to have in common? They have the same genus. Do they have the same species? The same kingdom, phylum, class, order, family? The same kingdom, phylum, and class only? Or the same family, genus, and species only? They're going to have the same kingdom, phylum, class, order, and family. And this is why. This is also why knowing your mnemonic device is going to help you out so much, because you need to know the levels in order. So kingdom, phylum, class, order, family, genus, species. So we look at these two organisms, we determine they have the same genus. So they're in the same level here. If they're in the same level here, they must have all of these in common. Okay? Because remember, these levels fit into each other like Russian nesting dolls. So if you're in the same thing here, if two organisms are in the same Russian nesting doll of this size, they must also be in the same of that size, and of that size. Okay? But just because they're in the same here does not mean that they're in the same there. Okay? Same thing here. If they have the same genus, they have the same all of those. However, they could be different species. We don't know. Okay? If I tell you, or if you learn, if you deduce, if you're looking at a problem and you determine two organisms have the same order, they have the same order, they have the same everything above it. Okay? If two organisms are in the same kingdom, they must also be in the same domain. Okay, let's move on from our review. So what exactly is a cladogram? So all living things on Earth can trace their descent back to a common ancestor. That's a part of evolution that we learned, right? We learned all living things can trace their descent back to a common ancestor that is now extinct. So today we're going to look at what is called a phylogenetic tree. And a phylogenetic tree is essentially just a diagram that represents the evolutionary history and the relationships of a group of organisms. So a cladogram is a branching diagram that represents the evolutionary history and relationships between different organisms. So cladograms are designed to show us how closely related different species are to each other. So cladogram can look like this, right? These are the taxa. So it could be species, it could be different kingdoms, it could be different phylums. We don't know. We're just going to say just taxa A, B, and C. Okay, by looking at the cladogram, we can see if we trace the history back. This right here is the common ancestor of A and B. And if I trace it back even further, that's the common history of A, B, and C. So cladograms can look, in different ways. These are all cladograms. So essentially what they have in common is that they have some sort of primary branch in which they have smaller branches that come off of it, right? So these are branches, and then there are smaller branches that come off of that, right? Same thing in all of these. They all have taxa. So in some of them, there's just organism names. Some of them have specific species names. Okay, they have just different taxa. And they also tell you about the different characteristics that the organisms share. So we're going to look at how we actually are going to build and read them. So again, cladograms are built by looking at shared characteristics. So what organisms have in common. So let's say we have lancelet, lamprey, tuna, salamander, turtle, and leopard. We have these different organisms and we're organizing them in based off of what they have in common with each other. So we have a primary branch, and again, then we have these secondary branches that come off of it. So on the primary branch, we also have listed some characteristics of these organisms. Okay, if I take my finger and I start here at the beginning, everyone sees down here where I'm talking about this is the beginning, and I'm going to move my finger along, and this is showing time. So over time, this is happening. So as I pass something, for example, I just passed vertebral column. That means every organism that I now come across is going to have a vertebral column. So if I pass vertebral column, boop, I've passed lamprey. Lamprey has a vertebral column. Okay, I'm going to keep going. Boop, I've passed tuna. Tuna has a vertebral column. I keep going. All of these organisms have vertebral columns. Okay, if I start again at the beginning and I keep going, boop, I've passed jaws. Does a lamprey have jaws? No, because I got to lamprey before I ever even touched jaws. So they do not have jaws. But once I pass jaws, tuna has jaws, salamander has jaws, turtle has jaws, and leopard has jaws. Okay, how about 4 walking legs? Does a tuna have 4 walking legs? No, because tuna branches off before I have 4 walking legs. So 4 walking legs applies to salamander, it applies to turtle, and it applies to leopard. Okay? So cladograms can be built by looking at physical characteristics. So for example, does an organism have fur or not? It could be built by looking at genetics or DNA. So the differences in cytochrome C. Cytochrome C is that, talked about it in the molecular evidence of evolution. Cytochrome C is just a type of DNA sequence that doesn't mutates very rarely. So it's very commonly used for seeing evolutionary relationships. Behaviors, so courtship singing or non-courtship singing. Does it walk upright or not walk upright, right? So those are different things that we can look at, some shared characteristics. Of course, there are more that we'll come across, but these are just ideas of characteristics that can be shared between organisms. They give us a hint as to their evolutionary history. So how exactly do we even build a cladogram? Well, let's look at this very simple one. I just chose one that's very simple so we can look at the different parts of it together and really break it down. So this right here is called the tip of a branch. This is called the branch, and this is a node. Okay, the place where the things intersect. An intersection, I'm bringing in math here, when they intersect, that is a node, and then where it continues on is a branch, and then there's a tip of the branch. Okay, this applies to all of these, right? So all of these are tips of branches. All of these are branches. And all of these little intersections are called nodes. So nodes are going to be the place where the common ancestors were, but those common ancestors are now extinct. The tips of branches are where we're going to have our taxa. Most commonly is going to be species, but sometimes it's not. Like I said, sometimes they'll put kingdoms up there. Okay, so let's look at this. So that was a very simple cladogram. Let's look at this one together. So again, we have our taxa at the end, so our groups of organisms at the end. We have all of our branches. We have a bunch of nodes, right? We see a bunch of nodes. And then we have a cladogram. Okay, one other thing to point out is that it's showing time. So this is showing over time. So this is very early, right? Because it's the very bottom. And then we're getting later and later and later as we go. So along the sides of branches are going to be where we have the shared characteristics. So This is what I kind of told you before, but I'm going to say it again until we get it. So we're started at this bottom of this branch long ago, and we're going to move along time. Over time, as organisms are evolving, they're changing, right? They're gaining characteristics. So right here, we cross over where we see there's organisms that are past this point all have hair, mammary glands, and lay eggs. So from this point forward, all of these organisms have this characteristics. Okay, so again, from this point forward, all of the organisms have placenta. One thing to note is that organisms behind this point do not have a placenta. They do not have a placenta. So here's an example. So I just simplified this by just calling organism A, organism B, organism C, and organism D to make it simple and easy. So what would we say that C and D have that A and B do not have? So answer choice A says hair and mammary glands. So let's go and find hair and mammary glands. Who all has hair, mammary glands, and lays eggs? That one does, that one does, that one does, and that one does, because they're all past that point. So that cannot be our answer. How about B, placenta formation? So let's see, who has the placenta? B has the placenta, C has the placenta, and D has the placenta. So again, that cannot be the answer to this question. All right, let's look at retractable claws. Let's go and find retractable claws. Boop, retractable claws are here. Who has retractable claws? C has it, and D has it. So C and D have retractable claws. A and B do not. Well, then that's our answer. So notice how I'm using this red dot to show you like where your fingers should be. And I literally recommend for you to take your finger, put it on the screen, and actually move with it. Okay? Because that's the number one thing about these taxonomy problems is that they're so easy, they're so straightforward, it's so simple to do that people always mess them up because they're just rushing. So don't rush these problems. There's no reason to rush these problems. You want to make sure you get 100% correct. Take your finger, put it on the screen, and then you'll get it right. You'll never get it wrong. If you take your finger and you follow along, you'll never get it wrong. Now, if you're just trying to look at it, you could possibly get it wrong. And when I say possibly, I mean probably, especially whenever we get to ones that are a little bit more complex. So go ahead and get used to putting your finger on it and actually moving and seeing, did my finger cross this characteristic or not? Okay, so again, the parts of the cladogram along the branches are going to be those shared characteristics. At the nodes of the intersections, we're going to have common ancestors that are now extinct. And at the tips of the branches, we have the organism names or the taxa. My foot is falling asleep. So let's do some more practice together. So again, here's another cladogram, another one that's pretty simple, because I just want to get you guys to know the basics. So which organisms have big ears? Well, let's look at this cladogram. We have organisms A, B, C, and D, and E. And then we have a branch, and we have a bunch of characteristics along it. So we're saying which organisms have big ears. So what we're going to do is we're going to start at the beginning of time, and we're going to keep going until we see big ears. Boom. Make sure your finger is on the screen. Then we're going to see what organisms have big ears. C does. Yep. D does. Yep. E does. Yeah, so C, D, and E have big ears. Okay, which organism evolved last? So again, this is the beginning of time, and this is how time continues. So which organism evolved last? E. Does B have a fuzzy tail? Yes, it does. You pass fuzzy tail, and then you pass B. So B is included in the fuzzy tail. Okay, another way of looking at this is like this. So as you're passing along fuzzy tail, organisms B, C, D, and E all have a fuzzy tail. Okay, you pass along big ears. After that, you reach organism C, D, and E, so they all have big ears. Once you pass whiskers, organisms D and E all have whiskers. It's another way of looking at it if you're more of a color-coded type person. So I have a question. What is located at this node here? Common ancestor of A only, of B only, of A and B, of A, B, C, D, and E. That is going to be the common ancestor of A and B. How do I know that? Well, I'm just going to take my finger. B, A, they meet up here. That's their common ancestor. No other organism, like I can't draw a line from C and then, like, no, that doesn't work. A and B, boom, easy. Okay, let's say if I'm looking for the common ancestor of A, B, C, D, and E, then I'm going to find all of my taxa and I'm going to go to their most recent node. So I'm looking for the common ancestor of A, B, C, D, and E, just for demonstration purposes. Then I'm going to go to E, boom, right here. That's where E's most recent node is. A, boom, right here. D's most recent node is there, but does that match up with the rest of them? No, so I have to keep going. Boom. B, same thing. C, same thing. So they all meet up there. That's where the most recent common ancestor of all the organisms is. If I ask you for the most recent common ancestor of A, B, C, and D, well, then I'm just going to take my finger and meet up there. So again, really drilling this point. These are the species of interest that we are looking at. We have our most recent common ancestor of A and B. We have the most recent common ancestor of A, B, C, and D, and E. Okay, one thing to also remember is that we're going against time. So this is long ago, more modern day. Okay, also know that a cladogram can look in basically so many different ways, but it all has the same information. So again, we have our species of interest, we have our traits, and then we have our common ancestors. Okay, so just know that there's different ways that they can look, but they all have the same information, and you should be able to get the same information from all of them. Same thing here. It looks different again, and that's why I say some of them can get really complex, can get really confusing. So that's why I recommend to take your finger, put your finger on either the species that they're talking about in the problem or put it on the characteristic that they're talking about. Put your finger on it and actually move and go back and go forth and do whatever you need to do. So this is the virtual worksheet. So the very first part of it is going to be about the intro to taxonomy. So you're going to have some recap questions on that. And then have cladogram problems in which you're going to have to tell me about the tips, the nodes, and all of that. Okay? You're going to have to actually look at some cladograms and give me the information from them. So go ahead and get started.